Okay, now we will go into our discussion on waves. No, so we've covered this. We've started discussing this one already. No, and our discussion on waves again. No, it tells us about uh, they are significant in physics because they carry the energy. No, with them. No, so as the energy is being transmitted. No, we let it travel from one point to another. No, that's how crucial are waves. No, again, now we've started mentioning this last time, and we have mechanical waves. Those that in needs, no, it needs a medium for them to be transmitted. And examples of mechanical waves, no, which are very common, is my voice. Sound wave is one. Water waves, no, the one that we see in the ocean or on the shoreline. No? These are waves that we need. No, we need some kind of water, no, or string, not to be able to visualize the wave. No? Now, electromagnetic waves, on the other hand, no, are kinds of wave that do not need medium at all. No? So they are kind of different from our mechanical waves. No? So light is one. No? So light is actually a part of a very long spectrum of wave we call as EM waves. No? So this is the wave that is actually coming from the sun. No? So the wave coming from the sun, no, is actually very long. There's this very harmful and high energy waves called gamma rays. No? On the far end are the radio waves or the infrared waves. No? That are also no, considerably dangerous. No? But anyway, we use this for communication, the ones with the longer wavelength. No? And somewhere in between that, no, a very short wavelength or span of spectrum is known as the visible light. This is where our eye, no? This is the only portion of the wave that is visible or noticeable or that can be observed by our eye. No? So again, no, waves, um, electromagnetic waves, no, include the light. No? And we know the speed of these electromagnetic waves to be around 300 million meters per second, no? Equivalent to the speed of light actually. No? Because again, no, they are just one in the same wave. No? So waves are basically, no, disturbances. So if you have a pond of water and you see that you touch one end of that water, you'll notice that after a while, the entire water in the pond are now, no, disturbed. No? So that's what we see with waves. No? So waves start out small and then they spread out in all directions. No? So they move in all sorts of directions. No? So it's a short, no, for the waves is it's a disturbance. No? And some of these disturbances require a medium like water or string. No? Now they have velocities as well, no? So they appear to be moving outward, no, from where they start and then they go outward. No? Some of them are shaped circular, some of them are shaped parallel to each other. No? And when you jerk a string, for example, you see a pulse also. No? So if you strum the guitar, no, the strings of the guitar, you'll see it vibrating. So that vibration, no, where you hear some sound, is known as a wave, no, or a disturbance. No? So again, we have several types of medium, and common to this is the string. No? The piano is also, no, an illustration of a string instrument, no? Where you disturb the strings of the piano to hear its melodies or music. No? Now for our types of wave, no, we have transverse and we have longitudinal wave. No? So what are transverse waves? No? So if you notice, no, that if we will jerk the string again, no? So initially it's straight, but when we move one end of that string, it creates a pulse, and that pulse now seems to be traveling like in an S-shaped manner. No? So it looks like an S shape, especially if you keep on moving point A, no, up and down, and then you'll see these strings of S shape like uh, vibrations. No? So if you only create one, then you can probably call it as a pulse. No? Now, The movement of A and B and C, no, which are particles of the wave, are simply moving up and down. No? However, this wave is appearing to be moving from left to right. No? And therefore, no, because of the perpendicular motions of the particles A, B, C, D with that of the wave motion, then we call it as transverse wave. No? So there seems to be not two motions involved here, and they are moving in perpendicular manner. No? So the string basically is an example of our no, our transverse wave. No? Now another illustration will be this slinky. No? So slinky is when you bob the slinky up and down, then you'll notice that it will be moving left to right. No? Now the lengths of these two lower portions no, are called your wavelength, no? Or this is the two no, in phase points, and then therefore we consider that to be a wavelength no, of our given wave. No? And they can be measured in terms of a unit of length in meters. No? Now longitudinal waves, on the other hand, no, travel in a different manner because if particles are compressible, no, like water or no, like air, no, if air can be pressed together, no, then therefore now we can see that we can produce no longitudinal waves. No? Now longitudinal waves now when you have air columns like this, so initially the air columns are spaced equally apart. No? So this is the equilibrium state of our um, air columns. No? But when I start to talk, most likely this particle or this column, air column A, will now move near B. No? So that's not its equilibrium state. However, because of the disturbance I create at point A, it now moves nearer to B or to C. No? Now, those that moves near, no, the air columns that moves to the right, no, towards our columns A and B and C, will now restore themselves. So they will try to go back. No? However, since you move A here initially, B will now try to distance itself from A. No? So therefore, it will go near to C. However, when B goes near to C, A is already returning to its place. No? Therefore, A will be a little bit further from B. No? But B and C will now be compressed together. No? So this series of motions no, that stretches columns or particles apart and near each other are called a series of compressions and rarefaction. Now that one will happen in a very short period of time. And therefore, no, you hear the voice of a person no, in a snap. No? You don't hear it no, as like this, no, that it will really take time. No? So our voice travels by longitudinal no, wave illustration. No? Now, our uh, our difference of our longitudinal wave is that the wave particles move left and right, and the wave motion is also moving from left to right as well, that they appear to be moving no, parallel to each other. No? So because of this parallel motion, then we will have no longitudinal kind of wave. So a series of compressions and rarefactions of the columns of air are therefore considered as longitudinal wave. No? So here's another illustration of that one, no? Talking about no, compressions and rarefactions. No? So an example of longitudinal wave is of course our sound wave. No? Now surface waves are the ones that we see in the ocean. No? It seems to be that they are rolling. No? So they roll. No? This particle seems to roll no? Up and down, no? But actually they are just going in that manner. But seems that this wave no, is traveling no, from the ocean to the shoreline. No? But actually, no, the wave particles there are simply rolling no, and turning. No? So the lowest point of the wave is trough, and the highest point of our wave is known as the crest. No? Two crests is equivalent to a wavelength, or two troughs also is equivalent to a wavelength. So this is another trough. This is another trough. If you get the distance there, we call that as our wavelength. No? Now, properties of our wave. No? The highest point, which is the farthest distance away from the equilibrium point, is known as the amplitude. No? The distance of two in-phase points, or like two crests together, or two trough, is wavelength. Now, the time it takes for one wave, no, or one wavelength to be produced is known as the period. No? This one is expressed in a unit of time, no, called seconds. No? So how long will one wavelength be created? That's equivalent to what we call, no, a period. We symbolize that with letter T, capital letter T. No? The frequency is in small letter f. No? And the frequency is the number of times, no, in 1 second, no, how many waves are created in a matter of 1 second. No? Now, the product of the wavelength times frequency is known as the wave speed, or the velocity of the wave. No? So wave speed is in terms of v. No? And again, no, v is written as, no, so the wave speed v, so that's your wave speed, it's equals to lambda, no, which is an inverted y, times f. No? So let me just draw our lambda. Lambda appears to be like this. No? So that's in a unit of meters. No? Or another way of writing our velocity, no, is equivalent to uh, wavelength over period. No? So v is written also as, no? So if you'll use the period, so t there is our period, and our numerator now, no, we can write our numerator as the wavelength. So again, the lambda symbol, no, the one that looks like letter y, no, this one is our numerator. So v is our speed. Now, in terms of frequency and period, no, so frequency, or the period, is 1 over f. No? So if you divide the ratio of our frequency to our period, no, then they are, no, then we can actually, no, write them, no, to be the reciprocal of each other. No? Okay, so no? So frequency is the number of waves produced in a matter of a second. No? Okay, now let me erase these diagrams. No? So I'll just erase that one. No? Now here is the characteristics. No? So the highest point from this equilibrium line to the top, that's what we call amplitude. No? But these two lower points, no, which we can think of as amplitudes as well, no, but going down. So the lowest points are trough, the highest points are crest. No? So the troughs and the crest, no, if you measure it from the equilibrium line, that can constitute your amplitude. No? But the distance of these two crests, or two troughs, no, is equals to a wavelength called lambda. No? So this is the one that we denoted earlier as the letter y. No? So we call that, again, on the word lambda. Again, some of these points, you can literally see them to be together. No? So the points that are together are called in phase. No? So like points 1 and 9, they are going together. No? So they are in phase points. So therefore, they can be measured, no, as equivalent to a wavelength. No? So that's one complete wave, by the way. No? So from the starting point going here, going and then ending there, no, you'll notice that the wave will start again, no, with the same pattern. So meaning from 1 to number 9, that's one wavelength. The time for it to be formed is known as a period. No? Now, if from 1 up to this end here is equivalent to 1 second, then we actually form two waves. No? So two cycles in 1 second is known as frequency. No? So if you consider this to be 1 and then 2 cycles, no? If that happens in a matter of a second, then we can call this as a frequency, no? 2 cycles per second, or 2 hertz. No? So some units of our no, unit of time, no, or unit of frequency, no. I will ask the class to send their name, no, in family names, please. Unless there are two, no, of you with similar family names, please send your names in Canvas, in our GC, no, so I can check the attendance later on, no, despite the fact that you may probably go offline, no, when we start our exam, no. So by 8 o'clock, we will start our test for 4. I think that's not really, no, very long. So kindly complete that, no, ang atong test, no. So I call it a synchronous activity, no. Can you view the activity already, no? Is it visible, guys?
8 na, sir.
Yes or no?
Accessible, sir, 8.
Para nakita na, no? Naka-post na siya, di ba? Okay, so it will not probably include, no, waves, guys, but atong previous lessons lang, no? I think in the problem solving, nadala ang first condition, no? So sa exam na lang na guro, ihatag ko na lang na next pagid nga exam, no? So after our quarter exam next week, no, I will still give you, no, some other rounds of examinations, no. Okay, anyway, now going back, no. So particles 1 and 5, no, have the same displacements. So these are some features of our wave, no. So successive points are called in phase points, no. So here are equations that we can have, no. So this triangle illustrates that speed is the product of frequency and wave, no. F times lambda, no. So I already wrote that, no. So for example, number 1, a wave has a frequency of 10 hertz. So this is frequency, and the wavelength is 30 meters. So you can simply multiply it, no. So 10 times 30 is 300, but the unit now will become meter per second, no? So number 1 is simply the product of 30 times 10. Hertz is a unitless value, therefore the answer here would be 300 meters per second, no? Number 2, no, if the frequency in question number 1, no, is changed to 20 hertz, what is the wavelength of the wave, no? So if the speed there is 300 meters per second, no, from number 1, and if that's constant, no, how do you get the frequency, no? So if you will solve for frequency for number 2, then that's speed divided by wavelength, no? So again, no, I don't know. If you're solving for wavelength, no, so how do we get the wavelength, no, for number 2, no? So wavelength is this is equal to, no, how do you solve for wavelength, no? So that's speed divided by, no, frequency, no? So therefore our value there, no, will be to have, no, 300, because we solved it in number 1 to be 300, and then we divide this by 20, no? 20 from 20 hertz, no? So what's 300 divided by 20? That is equivalent to 15, no? So our new wavelength, no, if we change the frequency to 20 hertz, no, and the speed is the same, no, then therefore we'll end up with 15 meters, no? So again, no, for number 1, V is simply, no, from the triangle, that's wavelength times F, no? That's how we get our value there, no? Okay, now number 4, we have a speed, and then we have a frequency. So how do you get a wavelength? Wavelength will be, no, again, the same as this one, no? V over F, no? So that's for number 3, no? Now, I think roughly, no, ang speed of sound in air is around 320, I guess, no, more or less, no? But since this is now in water, so probably sound will travel a little bit faster in in water, no? Because water is much more denser, no? So therefore, no, you have there the speed, and if you are given the wavelength, no, given in number 3, then you can solve for the given frequency, no? Okay, so a fisherman notices one wave, no, passes the bow, no, of his anchored boat, no, every 3 seconds, no. So meaning if that's how fast the wave is moving, maybe this 3 seconds is the period, no. He measured the wavelength to be 8.5 meters. So how fast is the wave traveling? So ginapangita iya ang velocity, no. So in this problem, we are looking for velocity. But again, no, 3 seconds is the period, no, t. So how do you solve for the velocity? So that will be wavelength divided by the period t, no? And the value will be, no, 8.5, no? That will be 8.5 meters divided by 3 seconds. And our unit there would be in meter per second, no? Ang aton answer, no? Okay? So this is for our, no, number 1, no? And again, no, the only thing that we added here is the term period, no? So Vt is equal to your lambda, no? Okay, now what are wave fronts? No? Ano naman yung wave fronts na ginamit natin? No? So this is the end of the wave, no? Ang aton wave fronts. And some of the wave fronts that we know are circular in nature, no? So ano yan, ang punta yan, mo niya itong ginatawag na wave fronts, no? Now when we drop something in water, no, makreate gina siya sang circular nga wave fronts, no? But kung ruler ni aton ni butang, if you drop a ruler here in this clear or still water, no, then we'll create also parallel lines, no? Okay, so those are the advancing wave fronts, no, that you see, no? And then again, this one is always going outward, no? Unless otherwise there's already a surface there which this wave, no, bounces and already returns, no? And then you'll see now interference of the waves when the outgoing waves, no, are being, no, it encounters the reflected waves already, no? And then you see the water there, no, that is getting turbulent, no? So again, now this clear image is called as a ripple, and these advancing waves again are called your circular wave fronts, no? So wave fronts can be explained by this Huygens principle, no? So we call their S as the point source, no, of the disturbance. Probably this is where you dip your finger or you drop a stone, no? And then again, no, from there, the direction will be in all directions together, no? Since it's a simultaneous movement of the particles, then they will appear circular in shape, no? Okay, so they will move outward, no, in all direction. So again, no, a point source of a disturbance will now create circular motions, no? Now again, no, this is Christian Huygens that tries to, I think they pronounce it as Huygens, no? So they have outward, no, distribution of the wave, no? So Huygens or Huygens, no, is this try to make an explanation why it is circular in shape, no? Now refractions or reflection. So when a wave, no, strikes a surface, no, like what we have there, then it will bounce back, no? Echo if it is sound. If it's light, then it will appear like this, no? And you create an image if it's a mirror, no? Now, some of the waves there, no? If this is air and water, some of the waves there will penetrate through water, no? And then therefore you'll see a bending of that wave, no? So we call that as refraction, no? Now, since the water, no, is more dense than air, then the tendency of this wave is to bend towards the normal line, no? Now, the angle of the incidence there, no, and the angle of reflection for the wave that reflects back, no, up, no, in the air, will have two equal values, no. So the law of reflection tells us that this angle of incidence and this angle of reflection are two equal values, no. Now, interference is when waves come together, no. I think light interference produce varied colored lights, no. So if you mix, no, a white light with another color, no, or two colored lights together, you'll notice that once they come together, no, they produce another new color, no. So again, no, interference, no, when they come together, no, ang varied kinds of wave. Some waves will now get louder, no, if it's a sound, and we call that as a constructive interference, no. So these two smaller disturbances, once they come together, no, produces a louder sound, no. But on some occasions, they can also, no, cancel each other. So if this wave, no, is going up, but this one, the other wave is going down, and then when they come together, they produce, no, a muted sound, which we call as a destructive form of interference, no. Now, some forms of interference for sound, no, produce the beat, no, of the drum, no. So those are also examples of interferences, no. When you hear, no, some kind of timing, no, or of the wave, no. Now, acoustics is the study of sound, no, in physics, and we realized that we can actually, no, make a room, no, produce lesser echo, no, if we know how to use the uh, vibration there, no. So waves travel in this medium, no, water, metal, no, and many other forms of bodies, no. Now the intensity of the sound is how painful you hear the sound, and it's dependent upon the power of the sound, no. So how intense it is, no? It is the power that is pressing on a particular area, no? And usually that intensity of the sound, no, will either if, cause an effect on the how no, no, how you perceive the sound, no? Sound waves is affected by temperature or sound velocity, no? So maybe warmer, no, environments will produce a faster traveling of the sound, no? Now, we call the reflection of sound as echo, no? And sometimes we don't want echo, no? Especially if it's in a room like an auditorium, no? So what do they place on the surfaces of the auditorium? They put, no, some soft surfaces or irregular surfaces, no? Refraction of sound is observed when sound is bending, no? Like at night, sound is believed to be bending towards the ground, no? So that's why at night you don't really need to shout, no? You can just talk softly and you'll hear the person immediately, no? But at daytime, the sound is going upward, no? So that's also the refraction of sound whenever it's night or on it's daytime, no? Resonance of sound is when two objects vibrate, no? Because they have an almost similar frequency, no? So resonance is occurs, no, when objects of almost equal frequencies, no, will try to vibrate, no, whenever you let one, no, vibrate. Only one of them is vibrating, but the other one is affected, no. We call that as resonance of the sound, no. So this tuning fork, for example, so if you vibrate one, and if they have the same frequency, you'll notice that the vibration here will transfer to the other tuning fork without even, no, touching this tuning fork, no. So we call that again, no, as resonance, no. We use the idea of resonance in communication, no. Now Doppler effect is the one when you hear an ambulance, no. As the ambulance goes near you, you'll notice that the frequency of the sound produced by the ambulance gets, no, higher and higher in pitch. But by the time it passes you by, you'll notice that the pitch of the siren of the ambulance goes suddenly drop, no. It will just simply drop, no, down, no. So doon nagulpi lang nga nubo ang iya pitch, no. Again, no, approaching, it has a higher and higher frequency or higher pitch, but as soon as it passes you by, then suddenly it drops down, no. Now we call that phenomenon as Doppler Doppler effect. No? Maybe the same is true with the train. No? As the horn of the train no, comes towards you, you hear a greater frequency. No? So man, no, it's because this one is moving and the observers are stationary. No? So that's how we characterize no, the Doppler effect. No? Okay, so I think you can study this one no? Because these are all up in your canvas already. No? So